Hey everybody, let's talk about valence bond theory today. When people are trying to explain covalent bonding, there's a lot of different levels you can take it to. So far we've just said covalent bonding is due to the sharing of electrons, and we can use valence shell electron pair repulsion theory, this idea that electron pairs that result are going to repel one another to predict geometry. But while that's very useful and it works for a lot of situations, it's not the full story. So we're going to take this one level up today, and then there's another level still to go. So valence bond theory is very useful, but it's definitely not the whole story, just like via CPR was not the whole story. So what valence bond theory says is that you can actually explain that bonding as an overlap of atomic orbitals. So we know our electrons are in orbitals on the atoms. We've talked about all the electron configuration, where to find them. So what this is saying is that bonding occurs when these orbitals that contain electrons overlap with one another, concentrating the electron density between the atoms. So if we take a look at hydrogen, if we have two hydrogen atoms, we're going to form H2, the simplest possible compound. You have an atom, each of which has electron density in this spherical 1s orbital. When these come to overlap, you end up with a buildup of electron density between your nuclei, and this results in a bond. Sweet. And so this overlap of electron density is what valence bond theory considers a bond. And it makes perfect sense for hydrogen. These two spherical orbitals come over and overlap. Fine, no concerns. If we take a look at a slightly more complicated molecule like methane, CH4, if you look at where your valence electrons are, and it is definitely still the valence electrons that are involved in bonding here, carbon's electron configuration is 2s2, 2p2. So it has electrons in the s and in two of the p orbitals. And then each hydrogen has a 1s orbital with an electron in it. When the carbon bonds to the hydrogen, we know from experiment that all carbon-hydrogen bonds end up equivalent, and they are arranged at 109.5 degree bond angles from one another, because this would be a tetrahedral geometry. How can we accomplish this bonding when carbon has 4 different shaped orbitals and 3 of those are at 90 degrees to one another? There must be something going on here, or we need to do something to explain the fact that all the bonds end up being equivalent to one another. And so what we're going to do is called hybridization. We're going to take the orbitals on carbon that are available for bonding from the 2s and 2p orbitals, and we're going to blend them together to get a result that will be consistent with the experiment, because it is going to give us 4 equivalent orbitals. So how are you going to decide how many orbitals you actually need to mix up in order to get ready to bond, and what the result's going to be? We're going to kind of go back to where we started with our VSEPR process, which is we are going to look at how many regions of electron density we have. And so if we have 2 regions of electron density that we need to accommodate, that means I'm going to need 2 equivalent orbitals. 2 hybrid orbitals. And so we'll take the s, because it has the lowest energy, and one of the p's, and we'll blend them together. And you get an sp hybrid orbital. And an sp hybrid orbital looks something in between an s and a p. And so these orbitals have a large lobe and a small lobe. And these 2 hybrid orbitals are at 180 degrees from one another. We only had to use one s and one p, so there remain 2 unhybridized p orbitals. If, on the other hand, we need 3 regions of electron density, we're going to use 1s and 2 p's. That gets us 3 regions of electron density. So we'll use an s, one of the p's, and another one of the p's. And so when you blend those together, you get 3 sp2 hybrid orbitals. And these sp2 hybrid orbitals lay at 120 degrees from one another, just like you would have seen for a trigonal planar geometry, so 120 degrees from one another. And we still have 1 unhybridized p orbital remaining. Kind of keep that off to the side. If we need to have 4 regions of electron density, so we say have a tetrahedral shape, like our methane, we're going to need to use the s and all 3 p's. And so you'll blur all of those together and you'll get 4 sp3 hybrid orbitals, and these lie pointing towards the corners of a tetrahedron with a 109.5 degree bond angle, just as we would expect for something that will be tetrahedral with 4 regions of electron density. So if we come back to our methane, to our CH4, we can explain its bonding as bonding between the sp3 hybrid orbitals on the carbon and each hydrogen's 1s orbital. So if I just draw the large lobes, because those are the ones that are involved in bonding, we can talk more about that in class. For the carbon, these will overlap with the 1s orbitals on each of the hydrogens to form these little bonding interactions that result in that overlap of atomic orbitals and a bonding interaction, a covalent bond. If you have something like ethene on the bottom left down here, C2H4, where you have a double bond, you look at this carbon, we can determine the hybridization on each carbon. This first carbon on the left has 1, 2, 3 regions of electron density, spp, so sp2 hybridization. The other carbon has 3 regions of electron density as well, so it is also sp2 hybridized. On the right-hand side, we have acetylene, or ethine, if you're going to name it by IUPAC standards. And so this needs 2 regions of electron density, sp. So each of these carbons is going to be sp hybridized to have those 2 regions of electron density. You should be able to look at a carbon, an oxygen, or a nitrogen and determine its hybridization by counting regions of electron density around it. Lone pairs count, just like they did for geometry stuff that we were doing before. There's one more thing we need to talk about with valence bond theory. We've said that we are going to hybridize our orbitals to ensure that we end up with geometries that are consistent with what we see in an experiment and equivalent bonds when we're forming multiple bonds. We also need to talk about how that overlap of orbitals is occurring. In our example of CH4, the hybrid orbital on the carbon and the s orbital, the unhybridized s orbital on the hydrogen, are overlapping kind of in a head-on fashion, where the electron density is concentrated between the 2 nuclei. This is called a sigma bond. In a double bond or in a triple bond, you do have a head-on overlap of the hybrid orbitals. So for example, in the carbon-carbon double bond situation, you had an sp2 hybrid orbital overlapping with another sp2 hybrid orbital. So here's all my sp2 hybrid orbitals on each of the carbons. And so you have a sigma bond formed with that. But if you recall, I said that we had some unhybridized p orbitals that remained because you only used 1 s and 2 p's. There was another p orbital remaining. That p orbital on each of these carbon atoms that I just attempted to sketch in blue down here, these can overlap with a side-on overlap. This is typically a weaker bonding interaction than a sigma bond. We call it a pi bond. And in this situation, we have our electron density still between the atoms, but above and below that internuclear axis. When you have a triple bond, you actually end up with the single bond from the overlap of the hybrid orbitals. There were 2 unhybridized p orbitals, and each of those are going to be able to overlap. They're at 90 degrees to one another, but you're going to get 1 pi bond for, say, your py orbital overlap and 1 pi bond for your pz orbital overlap. I'm going to attempt to draw this. I promise we'll look at some prettier pictures in class. So in this picture, I drew just the pi bond to try to make it less busy. And so you see that we have a side-on overlap of our py orbitals this way, and then a side-on overlap of our pz orbitals. So we formed 2 pi bonds. So every time you have a multiple bond, like a double bond, you get 1 sigma and 1 pi from the unhybridized p orbital. In a triple bond, you get 1 sigma and 2 pi's. So when you go to look at a molecule and determine how many sigma and pi bonds you have, every single bond is a sigma bond. And within a multiple bond, you get 1 sigma bond. A double bond has a pi bond, a triple bond has an additional pi bond.